morning everybody. In the last lecture we had started with chemical energetics, and in that we had seen some introduction of this topic. We had seen what the thermodynamics is exactly, then the different laws of the thermodynamics, Gibbs law, first law and the second law. We had seen the objectives of the thermodynamics, limitations of the thermodynamics, and then we saw the laws. Then we saw the different terms which are used in the thermodynamics, the definition of the terms we had seen. Now, the different thermodynamic processes. The first process, that is the isothermal process. Now, what is the isothermal process? The isothermal process is the process in which throughout the temperature is kept constant. That process is called as the isothermal process. That means here in this process the heat is exchanged between the system and the surrounding. Therefore, the temperature of the system itself is kept constant. So, such type of the processes are called as the isothermal processes. That means in these processes, throughout the process, the temperature of the system is kept constant. Such processes are called as the isothermal process. The second type of process is adiabatic process. In this process, the heat is not allowed to exchange from system to the surrounding or surrounding to the system. So here in this process, temperature of the system does not remain constant. Here the system is insulated from the surrounding. So the process where the heat is not allowed to exchange between the system and the surrounding, that process is called as the adiabatic process. In this process, the temperature of the system changes because it is insulated from the surrounding, and therefore the heat is not exchanged between the system and the surrounding. The third type of process, isochoric process. The process in which there is no change in the volume of the system, that process is called as the isochoric process. So throughout the process, the volume remains constant. That process is called as the isochoric process. The next, isobaric process. In this process, the pressure of the system remains constant. That process is called as the isobaric process. Throughout the process, the pressure of the system remains constant. That is specifically called as the isobaric process. The next, the reversible process. Now, what are the reversible processes? Consider a process which is divided into many small steps, and in every single small step, the driving force and the opposing force, these two forces are infinitesimally different, and the driving force is infinitesimally greater than the opposing force. And in this small step, it can be reversed by increasing the opposing force by infinitesimal amount. Such processes are reversible processes. These reversible processes, they take place infinitesimally slowly. That means they are taking place at a very slower rate, and therefore due to this slow rate, the whole process can be divided into the small steps, and at every small step the driving force is infinitesimally greater than the opposing force. And if you increase the opposing force by infinitesimal amount, what is infinitesimal amount? That means a very negligible amount. If you increase the opposing force by infinitesimal amount, that small step gets reversed. Such type of the processes are called as the reversible process. So you can define the reversible process as the process which is divided into the small successive steps. At each step, driving force is infinitesimally greater than the opposing force, and the process can be reversed, or that step can be reversed, if the opposing force is infinitesimally increased than the driving force. Such processes are called as the reversible process. So how this process below here the gas is present. So this is the piston, and above this piston here I keep one vessel, and in that vessel consider that the sand grains are there. So in this process, due to first we had kept this, only the piston is there. Therefore, due to the moderate pressure of the gas, this piston will be pulled upward. Expansion of the gas will be there. So due to the expansion, this frictionless, very wetless and frictionless piston we have considered. This piston will move upward. And if we put again, consider now that piston has moved upward, and due to its moving, the expansion of the gas has taken. Now what we do, here we have put the sand grains in the vessel. We have taken one vessel and we have kept small grains of the sand grains. So due to the weight of the sand, the piston will again move backward, and if you take some of the grains outside, so the piston will move again, right? See, you keep the sand grains here on the piston. So due to the weight of the sand grains, this piston will move in the downward direction. And if you remove some of the sand from this vessel, therefore it will again move upward. So this is what is the reversible process. See, what has reversed? Due to the weight of the sand grains, the piston will move downward, and by removing some of the grains, if you remove some of the grains outside, so weight will decrease, and due to the decrease in the weight, this piston will again move upward. So the downward movement and again upward movement. So this process becomes reversible. We have taken a vessel in which you have kept a gas, and that gas is packed with the wetless frictionless piston, and on that piston you kept the vessel of the sand grains. Due to the weight of the sand grains, this piston will move downward, and if you remove some sand grains, that means you decrease the weight, this piston will again move upward. So this is what is the reversible process. So reversible process is where the process can be considered to take in a several steps, and in each small step the driving force and opposing force are infinitesimally different. If you increase the opposing force by infinitesimal amount, your step get reversed. Every such step can be reversed. So the whole process is called as the reversible process. Now the irreversible process. The definition, or what is irreversible process? Obviously, a process which occurs only in a one direction, that is specifically called as the irreversible process. That means that if you compare it with the reversible process, the process does not take place infinitesimally slowly. This is the first thing. How the irreversible process is different than reversible? The irreversible process does not takes place infinitesimally. It takes place at a faster rate. Therefore, that process cannot be divided into the successive steps. Or even if it is divided, a single step cannot be reversed as we were doing in the reversible process. Because in the reversible process, for a small step, the driving force is infinitesimal. That means it is greater by very negligible amount than the opposing force. Therefore, we were able to reverse that step by increasing the opposing force by infinitesimal amount. But in a irreversible process, that step cannot be reversed because the driving force and opposing force, there is a much difference in between these force, and that's why the process cannot be reversed. Such type of the processes are called as the irreversible process. That means you can The irreversible process are the process which does not take place infinitesimally slowly, and the successive steps in the process cannot be reversed. Such type of the processes are called as the irreversible process. Generally, all the natural processes are irreversible in the nature. For example, the transfer of a heat from hot body to the cold body. The another example, downhill movement of the water. So these are the examples of irreversible processes, and these irreversible processes cannot be reversed. So these were the processes, thermodynamic processes. Now, the next concept of standard state. What is the standard state of a substance? The standard state, actually these are the conditions of temperature and pressure. The standard conditions of temperature and pressure are 298.15 Kelvin. This is the standard condition of temperature, and 1 atmosphere. This is the standard condition of the pressure. So, when the substances are present at these conditions of temperature and pressure, that substance is said to be in the standard state. When the substance is present at 298.5 Kelvin and 1 atmosphere Kelvin temperature and 1 atmospheric pressure, that substance is said to be in the standard state. These are the standard conditions of temperature and the pressure. The standard temperature is considered to be 298.15 Kelvin and the standard pressure is considered to be 1 atmosphere. The elements, when the elements they are present in these at these conditions, their enthalpy is considered to be zero. For example, the hydrogen gas at this temperature and pressure, it is in a gaseous state. Its enthalpy is considered to be zero. The elements directly present in this state, their enthalpy is taken to be zero. Another example, the liquid bromine. The bromine at this temperature, it is present in a liquid state. It is in a Br2 state. The enthalpy of this bromine at this temperature pressure is taken to be zero. So the enthalpies of the elements, that means which are present in the nature as it is. So hydrogen, which is present as H2, bromine which is present as Br2 at this temperature and the pressure. The elements at this standard state, their enthalpies are taken to be zero. Now, the next concept of heat of formation. Heat of formation, or we can say it as enthalpy of a formation, which is denoted by delta Hf. Let's take one example. The formation of carbon dioxide gas from carbon and oxygen. This is the reaction. Carbon with oxygen forms CO2. Now here 1 mole of carbon dioxide will be formed from 1 mole of carbon and 1 mole of the oxygen, and the heat change which is taking place accompanying this reaction, that heat change is specifically called as enthalpy of a formation. So enthalpy of a formation is defined as the heat change accompanying the formation of 1 mole of a substance from its elements, that is called as the enthalpy of formation. The formation of 1 mole of substance, the heat change which is accompanying the formation of 1 mole of a substance from its element. That means here we can define the enthalpy of formation in concern with the carbon dioxide. So enthalpy of a formation of carbon dioxide is nothing but heat change which is accompanying the formation of 1 mole of carbon dioxide from carbon and oxygen is enthalpy of a formation of carbon dioxide. Now, the standard enthalpy of a formation, that is delta 0 H. Now, as the standard enthalpy of formation, therefore, what is standard enthalpy of formation? It is again the same, that is the change in a heat accompanying the formation of 1 mole of the substance from its elements in the standard state. That means when the elements are in the standard state, the formed molecule, when these are in the standard state and 1 mole of the substance is formed, the heat which is changed during this reaction, that is nothing but the enthalpy of a formation. So, for this reaction, the standard enthalpy change, the delta HF, this value is 393.5 minus 393.5 kilojoule per mole. So this is what is the standard enthalpy of formation for the 1 mole of a CO2 gas. That means here, when these two elements are in their standard state and there is a formation of 1 mole of carbon dioxide, therefore the heat change that is accompanying this formation reaction is called as the standard enthalpy of a formation, which is denoted by delta H0F. This is how the delta H0F is. Now, let's take one example. And this delta standard enthalpy of formation for a reaction, if we want to calculate, we can write the general formula as sum of enthalpy of formation of products minus sum of enthalpy of formation. Here, standard enthalpy must be given. Standard. Sum of standard enthalpy of formation of product minus sum of standard enthalpy of formation of a reactant. This is how you can calculate the delta H0 for the reaction. This is the significance of the standard enthalpies of formation. That means how you can find out standard enthalpy change in the heat for the reaction. It is equal to sum of the standard enthalpies of formation of product minus sum of standard enthalpies of formation of the reactant. If you know the standard enthalpies of formation of the product and the reaction, you can calculate the standard enthalpy of the reaction. So this is significance of delta H F0 value. If you know the standard enthalpies of formation of reactants and products, you can calculate the enthalpy for the reaction. For example, here, if you know these are the elements, right? So their standard enthalpy of formation will be 0. If you know the value of standard enthalpy of formation for CO2 and this reactant carbon and oxygen, and if you put them here, you will get the enthalpy of a reaction from this reaction. If you want to calculate delta H0 for this reaction, so So you must know the standard enthalpy for the formation of carbon dioxide, standard enthalpy for the formation of oxygen, standard enthalpy for the formation of carbon. If these values you know, you will get the standard enthalpy for the reaction. This is its standard enthalpy of formation is known. Now these are the elements. The standard state, in a standard state, carbon is in a solid form, oxygen is in a gaseous form, and their standard enthalpy of formation will be zero, because I have told you that the elements, if they are in a standard state, their enthalpies of formation are zero. So these are, we have considered this as in a standard state. So these are the elements, and therefore their standard enthalpy of formation will be zero. So for this reaction totally, standard enthalpy of formation of product, that is carbon dioxide, we know it is minus 393.5 minus. Now the standard enthalpy of formation for carbon will be zero, as well as oxygen will be zero. Therefore the enthalpy of the reaction is 393.5 kilojoule per mole. So generally, if we take a general reaction, like so for this reaction, delta H0 can be calculated as, see, summation of delta H0F of product minus summation of delta H0F of the reactant. So what will become? This is equal to, these products are this. So C into delta HF, delta H0F for C in plus small d into delta HF0 for D minus, for now reactant, A into delta HF0 for A plus B into delta HF0 for B. And if you know these values, delta HF0 for C, for D, for A and B, you can calculate the delta H0 for the reaction, that means the standard enthalpy for this reaction. Let's take one example. So this is the reaction. Let's balance the reaction. Now for this reaction, if we want to calculate the delta H0 for the reaction, so how it will be? Obviously, delta H0 for this reaction is equal to, here only one, first we will write for the product and then for the reactant. Summation of heat of formation for the product minus summation of heat of formation for the reactant. Therefore delta HF0 for CO2 plus delta HF0 for water. Now water, two molecules have formed, so 2 into minus delta HF0 for CO2 plus 2 into delta HF0 for water minus delta HF0 for methane plus delta HF0 for oxygen, the 2 into oxygen. So the values for this are minus 393.5 plus 2 into the standard enthalpy of formation for the water is minus 285.8 minus the enthalpy of formation of methane is minus 74.9 plus now oxygen. This is in a standard state, and as we have considered the standard condition, therefore the formation, the delta HF0 for oxygen will be 0, and this comes out to be minus 890.2 kilojoules. So this is how the formation, the delta is for the reaction